Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you. Raise your hand if you didn't get a red mark for today, the 15th. Okay, we are off and running with our final day of new learning in Unit 2. Today we're going to address arithmetic sequences and see how we can model real-world situations and find formulas that will give us terms in an arithmetic sequence. Two kinds of formulas we'll look at today. Explicit formulas, that's where we develop a function rule, where we can plug in the term number n and evaluate it in accordance with the function rule, and it'll spit out the term value, versus a recursive formula. A recursive formula, right, in order to find the current term, we need to know the term before it, and then we apply this rule, the pattern, right, again and again to develop more and more terms from the sequence. Each one of them has their benefits and each has their drawbacks, and that's what we're going to look at today. Next class period will be a review period, so you will have an opportunity to practice with all the things we've done in our linear functions unit. You'll have some in-class work time as you work and prepare for your review, and then leading up to our test on day 7. Our test then is on Thursday, the 22nd of October. So you want to make sure that you're gearing up and planning for that. So a week from today, next Thursday, will be your Unit 2 test. All right, to that end, let's go ahead and get cracking. If we have 2 points, we can determine its line, or the equation of the line connecting those 2 points, and we can write our answer in various forms, whether it's point-slope form or slope-intercept form, and you guys did a good job with this on your quiz. So let's go ahead and begin with point-slope form. With letters, we know that's my y minus y sub 1. Equals m times quantity x minus x sub 1, and we'll go ahead and figure out our n by doing our slope calculation. So thanks for using these points, and sorry about the typo. So we simply do 11 minus 3 all over 3 minus 1. And I get 8 halves. Raise your hand if you had 4 for your slope of the line. 4, everybody good? Great. Let's plug that in. So we'll plug in 4 right there. And we'll go ahead and rewrite y minus, pick one of my points to use. Which point would you like to use, Logan?
11.
311?
11, yeah.
So we'll do y minus 11 equals 4 times quantity x minus 3. Excellent. And now we can go ahead and box our answer because it just asked for point-slope form. So point-slope form, oh, wow. Look at that little guy. Point-slope form, right, is the quickest and most efficient way to generate the equation of the line. You could have used 1, 3, then you have y minus 3 equals 4 times quantity x minus 1. Raise your hand if you had either for letter A. You guys good? Great, thanks, hands down. We'll go ahead and box that since we want PDF-able. And now we'll go ahead and rewrite that in slope-intercept form. So this is just like a quiz question 2. In order to do that, we'll distribute our 4 through the parentheses in that second set. So I'll go ahead and keep my y minus 11, but on the right-hand side, I'll distribute through. 4 times x is 4x, minus 4 times 3 is minus 12. Adding over the 11 gives me y equals 4x, and it looks like minus 1. 4x minus 1, raise your hand if you have 4x minus 1. Did you get that already? Yes, you did. Good job, you guys. Way to go. What questions do you have about point-slope form versus slope-intercept form?
No questions.
Okay, so let's go ahead and take a look at standard form. Standard form, right, is that one where we model linear combinations with, right? The model of linear combinations, like the student ticket sales when combined with the adult ticket sales equals your total revenue for the play. And so what does that look like with letters, right? What does that look like with letters for standard form? Go ahead and tell the class. Adam? AX plus BY equals C. And so if we start out with 4x minus 1, y equals 4x minus 1, we can make it look like that. Right, we can make it look like that if we know that A, B, and C are integers, right? And A must be positive. So what I would do here is subtract over that x term to get on the left-hand side, trying to make it look like AX plus BY equals C, and we're close. It's just we wanted the additional requirement that A should be positive. And so what can I do to make sure that my value of A is positive? What can I do to both sides here? Eric? Absolutely. We can multiply through both sides by -1 and rewrite. So my final answer looks like positive 4x minus y equals positive 1, and we'll box that. What questions do you guys have about standard form? Standard form. The utility of standard form, aside from modeling linear combination situations, is that it's easy to find the x and y intercepts when you're in standard form and sketch a quick graph. Okay, so let's not lose sight of our rewriting formulas. Again, we can develop a recipe that'll allow us to solve for an indicated variable by considering our forward steps back from order of operations in middle school. So if we wanted to solve for v, I'll go to my equation and see which side v is on. Does it appear in the bottom of a fraction? No. Does it appear more than once? No, so we're ready to go with our forward steps. I'm going to focus in on the side that has the v, cover up the other side, and pretend that we're an expression I was going to evaluate by plugging something in for v. What would I do first? Well, if I plugged in something for v in order to evaluate that right side, I would square it. And so my first step would be squaring for a forward step, and then times by 1/2 m, or times by m, and then times by 1/2. I want to do it in 3 steps. All right, let's reverse it anew to get my solving steps recipe for success. If my last thing was timesing my 1/2, the first thing I'll do to solve is divide by 1/2. Keep in mind that divided by 1/2 is the same as multiplying by their reciprocal. So multiplying both sides by 2 will be my first step. Undoing multiplication of m, that's easy. I'll divide by m, and undoing squaring, that's where I need to consider the positive and negative, right? 2 possible answers when we undo our squaring, square root. Let's go ahead and apply those steps now. First step, times by 2. So both sides will time, oh, look at that. Did you guys see that? That was pretty sweet. So 2k equals mv squared. We got rid of the 1/2. Right? We got rid of the 1/2. Next, divide both sides by m. So we'll divide both sides by m, and that will get us 2k over m equals v squared. Finally, we can solve for v. What's going to undo the squaring? Considering the positive and negative square root. And this little 2 reminds me to be on the lookout for not 1 but 2 different answers. How do I get them? One's given by the positive square root, and one's given by the negative square root. So my final answer would be v equals positive and negative square root of the quantity 2k over m. Go ahead and take a look at this. And raise your hand if you had that already. So did anybody get to the end with the plus and minus? You guys are awesome. Way to go. I know you're going to rock style your Unit 2 test at the top. We've got one thing to add today, and that is explicit and recursive formulas for arithmetic sequences. But first, let's get you credit for your hard work outside of class. So at this time, please take out your assignment number 4. This did include the 2 reading questions, 3.6 and 3.8. I'd ask that you give yourself credit for those you complete out of 14. Divide, enter, multiply by 4, and if you completed your reading questions, you're eligible for an additional point, bringing your possible infinite campus score down to the nearest half point, 0 to 5. At the same time, please make sure that your name, first and last, 1A and number 4 are clearly labeled on top of your assignment. And if you need to staple multiple pages together, there's one on the front table and one on the side activity table next to the whole bunch. Please do so while we're grading it, and then when we're ready to pass in, everyone will be set. What questions do you have about your infinite campus score? Ben? Nope. Okay, no problem. Just classic teacher. Fake out. I just saw the pen raise. Bam. All right, so let's go ahead and pencil down. Pencil down. We'll go ahead and check our answers now with our grading pen. And soon we'll be advancing, so please make sure you're checking. Sorry about that. And next slide. Katie?
On the 1A,
Yep.
I got 30, but then if I check the back of the book and it says 34.
Okay.
So I like double check that it's still just 30.
So, for your formula, it looks like you're just off by one term, because 30, right, versus you got add 1 on 4.
Oh.
34,
Okay. Yeah.
$14. And we still need, nope, that's it. Awesome. Bless you. So as you're finishing up, go ahead and give yourself an accuracy fraction on how many you did, about how many did you get right. Circle that in pen. Make sure your infinite canvas score is boxed nice and big in pencil. Put your name first and last, 1A and number 4 are clearly labeled as part of your heading, and then kindly pass from the back to the front, please. Front rowers, make sure they're facing the same direction. I appreciate your help. Everybody good? Number 4. Thank you for your help, ladies and gentlemen. I appreciate that. It makes it much easier to record your assignment scores with your help grading them. Right now, I want you to focus in on your objectives for the day. So our last new content in Unit 2 will involve arithmetic sequences. So we're going to figure out what makes a sequence arithmetic, right, instead of just a regular sequence that you saw in last class's introduction to sequences. We're going to find explicit and recursive formulas for arithmetic sequences. We'll apply those to some real-world scenarios. And then we're going to recognize the properties of linear versus or arithmetic sequences. These mean the same thing. So if it's an arithmetic sequence, it's a linear sequence. There's a constant rate of change between successive terms like a linear function. And that's why we address these arithmetic sequences in our Unit 2, all about linear functions. An arithmetic sequence is a linear function. It's just discrete because there's isolated points that are disconnected, right? Okay, let's go ahead and get going then. Everybody on your note sheet, let's consider the following sequences. A sequence with a constant difference between terms is called either a linear sequence or an arithmetic sequence, right? Those are synonyms. So if an arithmetic sequence is the same as a linear sequence, then we're going to consider the difference between successive terms and see if there's a constant rate of change between them. So it's as easy as saying, okay, from 14 to 10 I went down 4. From 10 to 6 we went down 4. From 6 to 2 we get, you guessed it, down 4. So is this an arithmetic sequence? Absolutely. There's a constant difference, right? Addition or subtraction between successive terms. So yes, this is arithmetic. For number 2, consider differences between successive terms. That is adding and subtracting. From 4 to 8 we went up 8. No, up 4. That is numbers, sorry. From 8 to 16 we went up 8. From 16 to 32 we went up 16. Is there a constant addition or subtraction between successive terms? No. So guess what? Number 2 does not have, right, is not an arithmetic sequence. It's still a sequence, right? A sequence in math is just a list of numbers. Typically that obey some pattern. But that's not an arithmetic sequence because it doesn't obey the pattern of constant addition or subtraction between successive terms. Go ahead and figure out 3 and 4 if they're a yes or a no with your partner. Be ready to share with the class when I call in. So go ahead and determine if 3 and 4 are or are not arithmetic sequences. Be ready to share. Okay, so what do you guys think about number 3? Go ahead and tell the class what you and your partner decided for number 3. Olivia and Jackson? Yes. And what was your constant difference between terms?
Add 1 plus.
Add 1.5. Excellent. Add 1.5. I'm going to go ahead and label that as D, our constant difference, to set up for the next part of our activity. So D was 1.5. We went up by 1.5 between successive terms as we moved along the sequence from left to right. Great. What did you guys say for number 4? Thank you. What did you guys say for number 4? What did you guys say for number 4? Mark and Taylor?
No.
No. Raise your hand if you had no for number 4. No for number 4. Okay, and why did you say no, Mark?
The addition changes every time.
Yeah, there's certainly a pattern here, right? We've run into that pattern before in last class, but there's not a constant addition or subtraction between successive terms. We went up 3 and then up 5 and then up 7, so there's not, right? There's not a constant difference. It's not arithmetic. It's still a sequence, right? And we're going to learn about that sequence later, but for now, this was not an arithmetic sequence. Great. All right, now let's go ahead and connect our subscript notation. Recall the subscript notation for sequences. Use the above sequence to identify a sub 3. Well, a sub 3, you don't have this, I just want you to look. A sub 3, right, this refers to the value of the third term, right? What is the third term in this sequence? The third term. Brady?
5.
5 is absolutely right. A sub 5, right, what's the fifth term? That means the fifth term. What's that? Luke?
13.
13, thank you. What's a sub 1, right? A sub 1, Caitlin T?
-3.
-3, thank you. And a sub 8. Oh gosh. A sub 8. Well, is there a distinct pattern, right? A distinct pattern between these? Certainly. If we went from -3 to 1, 1 to 5, 5 to 9, could we figure out a sub 8? Absolutely. Everybody do it and be ready to share. So what are you guys thinking for a sub 8? Will? 25? Raise your hand if you have 25. 25? Nice job, you guys. So a sub 7 would be 21, and a sub 8 would be 25. Nice job. Okay, so who cares? Well, now we're going to develop a setup for recursive formulas, where we need to know what the subscript stands for. So remember what the index tells you. Consider a general sequence a sub n. If you're looking at a sub 2, what would the next term, right? What would the next term in my sequence be if you're looking at a sub 2? What would the next one be? Olivia? A sub 3. A sub 3, thank you. What's the previous term in the sequence? The one before a sub 2. Carson? A sub 1. Good. If you're looking at a sub 10, what's the next term? Right? What would the next term's name be? Katie? A sub 11. If you're looking at a sub 10, what would the previous term be? Right? What would the previous term be? Katie? A sub 9. Excellent. All right. So then if you're looking at a sub n, the nth term in a sequence, what would the next term in the sequence be? What would the next term in the sequence be if you're looking at a sub n? How can we write that? Katie?
A sub 1 or +1.
Absolutely, and that's where we get our notation for recursive formulas. I know that a sub n plus 1, right, is the next term in my sequence. I know that the previous term would be given by a sub n minus 1, right? Whatever n is, the term before would be called a sub n minus 1. Notice how this is in the subscript, and so it's not a sub n and then minus 1 on the baseline. This is down in the subscript. This is an index, a counter. It's saying 1 less than the current term number. All right, that's important because now we're going to go ahead and practice with our new notation. The recursive notation for an arithmetic sequence is easy to recognize because it has brackets, right? It has brackets. You need a starting value or a starting term value or term values. And then you need a rule that will give you the current term value based on the previous term's value. So a sub 1 is the first term. You need to know that. And then d is my constant difference. A sub n minus 1, as you just generated, was the term before a sub n. And so if I know the first term and the constant difference, it's easy to write a recursive rule. Let's go ahead and consider that sequence we just looked at. -3, 1, 5, 9, 13. Do I know the first term? Yes, so I'll tell the reader the first term. The value of the first term will be what? Ben C? -3. And now I tell the reader a rule that can be used to get the current term based on the previous term's value. So a sub n, the current term, would be gained by taking the term right before it, a sub n by minus 1, and doing what to it? If I wanted to know the current term value, I could look at the term before it and do what to that value to get the current term? Adam? Yep. Let's see, if I wanted to know what the current term is, I'd look to the one before it and do what to it to get the current? Add 4, absolutely. So a sub n would be given by a sub n minus 1, and then plus 4. This is down in the subscript, so this is down in the subscript. This is up on the regular line. You take the term before it and you add 4 to it. Would this work for 17? It would work for 17 because to get a sub 6, I'd look at a sub 6 minus 1 is 5. A sub 5 is the term right before it and do what to it? Add 4 to it. 13 plus 4 is, voila, 17. So a recursive formula, right, gives me a start value and then a rule to get the current term based on the previous term's value. Awesome. Let's write a recursive formula for the sequence given by 36.5, 33, 29.5, 26, etc. First thing I'll do is I'll consider successive differences. It looks like 36.5 to 33 would be, what is that, down 3.5? Is that going down 3.5?
Yeah.
From 33 to 29.5, down 3.5. From 29.5 to 26, down 3.5. Okay, so this is an arithmetic sequence, and I can write its recursive formula just simply by stating the first term and then giving a rule to get the current term value based on the previous term's value. Let's do it. Go ahead and tell the class a sub 1. That's the value of the first term when I call it. So what's a sub 1? Heather? 36.5. Thank you. The next thing the reader needs is a rule that will give us the current term, call it a sub n, based on the previous term's value. No matter where I'm looking to get the current term value, I'll look at the one right before it, a sub n minus 1, and do what to it? Right? What would I do procedurally to get the current term's value? Luke?
Minus 3.5.
Yep, subtract 3.5. So the current term a sub n is given by the previous term, a sub n minus 1, minus 3.5. It's that easy. I can recognize recursive formulas for arithmetic sequences because the second part of my definition will always have a plus a number or a minus a number, depending upon if my term values increase or decrease as I move along them from left to right. Adam?
So what's with the, like, for integers and so?
That's our domain restriction. It's saying that this rule only makes sense if I know the first term, right? If I don't know the first term, right, then this rule is not going to help me because I don't know the one before it. But once I get to the second term, then this rule works. I just look at the one before it, a sub 1, the first one, and do what to it? Subtract 3.5. For our purposes, we won't need that, right? You don't have to include that on your test or quiz for full credit. Because the rule doesn't make sense unless we have that first value. Great question. All right. Recursive formula for a sequence. Each term is calculated from the previous answer. We can generate a table by using the answer key in the home screen. So the example of recursive formula, if we gave you the formula first, a sub 1 equals 13, a sub n equals a sub n minus 1 plus 5. Let's list the first 5 terms. Okay? So what would the first term be? Right? What would the first term be? Well, are we given the first term? What's the first term, Casey?
13.
13. Thank you. So 13 is the first term. Now to get my subsequent terms, I need to look at, right, my second part of the rule. The second part of my recursive formula is a rule that gives me the current term value based on the previous term value. In order to find a sub n, the current term, I need to look at a sub n minus 1, the one right before it, and do what to it? Looks like add 7 to its value. So if I wanted the second term, I'd look at the first term, and I'd do what to it? I'd add 7 to it. So the second term must be what?
20.
20. It's that easy. To get the third term, I'll look at the one right before it, 20, and I'll do what to it? Add 7. To get the fourth term, you guessed it. Look at the third term and add 7. So have I gotten to 5 terms yet? 1, 2, 3, 4, 5, dot, dot, dot. This can be easily accomplished on a calculator as well. So if we had our calculator on my home screen, on my home screen, I could simply enter my first term. My first term was 13, so I'll enter that. Then I'll do plus 7, and it'll pull up the previous answer. Right? Plus 7, enter. Press enter again. Press enter again. Each time the calculator will add 7 to the previous term value. It's calling that answer the previous answer from the above line, which is exactly what we did by hand when we generated. So 13, 20, 27, 34, and you guessed it, 41. So we can generate that recursively by using our graphing calculator, and that's pretty cool too. Would you like to find the 25th term using this formula? Right, would we want to find the 25th term using this formula?
Sure.
Well, it's easy finding the 5th term, but to get the 25th term using this recursive definition, I'd have to, well, keep going and going and going. So I probably could do it, right? I just have to keep track. This would be the what term? 5th. So 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th. Oh, shoot. And now it's up. Oh, gosh. So now I don't know if I'm on the 25th. 19th, 20th. You know what I'm saying? So the idea is that, well, we certainly could. But we certainly could. But my idea is, yeah, we could, but I'd rather not.
It's 188.
188?
181.
188?
181.
Oh gosh, see? So the recursive formula works very well if I'm trying to generate the first several term values, but it's not so hot if I'm looking for a term value. All right, let's go ahead and try the next one. So let's suppose that a recursive formula specifies a sub 1 is 36 and a sub n is given by a sub n minus 1 minus 11. Go ahead and list the first 5 terms right now, right, and check with your partner. Be ready to share. Okay, what do you have for the first 5 terms? Braden?
36, 25, 14, 3, -3.
Raise your hand if you have the same 5 terms. The same 5 terms? Great. And did you do that by hand, Braden, or did you use your calculator?
I use my calculator.
Yeah, I think the calculator is a pretty sweet way to do that. It's easy if you just enter the first term value, 36, enter, and then your rule would be minus 11, and it'll pull up the previous answer. And this way we can generate 25, 14, 3, and so on. So thank you for sharing that. I appreciate it. Now let's go ahead and take a look at our little pop-up video question. Our pop-up video question is, would you like to find the 75th term using this formula? No, that would be a real pain. So we could have figured out the 25th term, right? As long as we kept track carefully, but it would be a real pain. And so this time, last time I said we could, but I'd rather not. This time I'm going to say, no, thank you. I'm going to say, no, thank you. Whoa.
778.
Good job, good job.
You actually, I didn't type the minus 11. You just do it. You just do it differently.
So that's why we have a catalyst for finding a secondary form. A recursive formula is great to generate the first several term values, but for high term values, I'd rather use an explicit formula. So a linear sequence is a linear function. If we look back at our Bellwork, we have an explicit formula. We could write an explicit formula for this arithmetic sequence, just like we wrote an equation. Did we write an equation, right? When we have 2 points on a line, yeah, if we had these as ordered pairs, we'd have the points 1, 3 for the first term. The first term, comma, term value 3. The second term would be 7. The third term would be 11. The fourth term would be 15, etc. So if we wrote this sequence as ordered pairs, where my input is term number, comma, output term value, I'd get 1, 3, 2, 7, 3, 11, and 4, 15. Do we recognize any of these points from before? Yeah, these are the ones that we changed, right? These are the ones that we changed for our Bellwork. So this 1, 3, and this 3, 11 could be used to find the same slope from our Bellwork, which was 4. We can write an equation Pointslope Form as we already did. Y minus 3 equals 4 times x minus 1. And then slope-intercept form, we would get y equals 4x minus 4 plus 3 is minus 1. And so this linear function that modeled the points for a line, number 1, can be used to generate the basic form for an arithmetic sequence, an explicit formula for an arithmetic sequence. A linear sequence is a linear function, so to write it, we can think about our Pointslope form that we did. We can go ahead and solve for y and generate our same exact form. Am I trying to add over y sub 1 in there? Yes. So I add over y sub 1 and then we group it together and it looks like voila. If we call it in our new sequence notation a sub n, it's connected to our same Bellwork. Okay, so y is called a sub n in the notation of sequences. Y sub 1, you guessed it, that's our first term, a sub 1. D is my constant rate of change, right? My constant rate of change or difference between successive terms, and then n is my input, it's my term number. Let's go ahead and summarize that as follows, and this one you guys did get, right? You got the box? Okay, so a sub n is given by a sub 1, that is the first term plus d times quantity n minus 1. Or an alternate form that most of you will like is a sub n equals a sub 0, the start value, the y-intercept, plus d times n. This looks a lot like y equals a plus bx for slope-intercept form. And so many of you will like the second form better because it doesn't involve the parentheses. A sub n is defined to be the current term. So a sub n is the current term value. A sub 1 would be the first term. T would be my constant difference. Positive if my terms increase. Negative if my terms decrease as I move along them from left to right. N would be my term number. And a sub 0 would be my 0th term, my ghost term. That's not actually a member of the sequence, but I can get by counting back one step. So while our sequences start with term 1, right, when n equals 1 for the first term, our preferred definition on bottom, a sub n equals a sub 0 plus d times n, we'd have to count back to a 0th term, a ghost term, to get that start value, the y-intercept that we're used to, and I think that's the easiest way. Let's go ahead and write an explicit formula for the arithmetic sequence 6, 10, 14, 18. First, we'll do a quick check. Between successive terms, is there a constant difference? Yeah, it looks like up 4, up 4, up 4. And so this is arithmetic. Let's go ahead and use our formula then to write an explicit formula for that sequence. So the first thing we do is we pick out our a sub 1. I know a sub n would be given by a sub 1, which is 6, plus my constant difference we just saw was 4, times my input is n minus 1. That would be this first form. Or perhaps one that we like more would be the second form. A sub n equals the 0th term plus rate of change, constant difference, times input n. So, or a sub n equals, my 0th term is not a member of the sequence, but could I get it? Yes, I'd count backwards 1. What would my 0th term be had it been here? 2. And so 2 5 would be my 0th term, and then plus 4n. Many of you will like this way better because it looks like our slope-intercept form, y equals a plus bx, where my initial value, a, is the 0th term in the sequence, and my bx now is my constant difference times input n. So many of you will like the box one. Some of you will like the squiggle underline one. In either case, though, it's easy to find the 25th term. The 25th term now, I'll simply plug in my term number for n and evaluate. Which formula would you like to use? The squiggle underline green or the boxed red?
The box red.
Boxed red looks simpler, doesn't it? Let's go ahead and plug in 25 in for n, and we can find the 25th term. So let's plug in 25 for n, and I get a sub 25 equals 2 plus 4 times 25. So I get 102. You guys get 102? Awesome. Guess what? The 75th term, a sub 75, would be given by 2 plus 4 times, you guessed it, 75. So 4 times 75, 300, so 302? Yep. 302? Awesome. So that was way easier than pressing my calculator button, right? 75 times and making sure, was that 73 or 74 or 75, right? And messing up. The explicit formula allows a function rule where I can simply plug in my input term number and it'll pair it with an output that's the term value. So if I wanted to state the first 5 terms of the sequence, right? The first 5 terms of the sequence in an explicit formula, I have to then do a sub 1 equals 5 plus 2 times 1 is 5 plus 2 is 7. A sub 2 equals 2 times 2 plus 5 is 9. A sub 3 equals 2 times 3 is 6 plus 5 is 11. And so on. So a sub 4 then, 13. A sub 5, 15. All right. So find the 75th term of the sequence, though, would be much easier. I just do a sub 75 equals 5 plus 2 times 75, and that in turn equals 150, 160. Is that right? 160? 155, I mean, 155. Good, thank you. I'm glad I did hold the class before I box that bad boy. All right. So which formula would you rather use, explicit or recursive, to find the 75th term of the sequence? Don't say it out loud. Which formula would you rather use to find the first 5 terms of a sequence? Why? Go ahead and decide with your partner and have a written response ready to share with the whole class. So our 2 choices are explicit and recursive. Okay, so which formula, explicit or recursive, would you rather use to find the 75th term? The 75th term of a sequence, which would you rather use? Margot?
The explicit,
Explicit, how come?
because you can enter any term into this without having to you only have to do one equation instead of having to do
Absolutely. You can use your equation and evaluate a single time when n equals 75, like a function rule. And so explicit would be the way to go if I'm trying to find the value of a single term, a high term value. Explicit is the way to go because it's easy to evaluate a function rule one time. would you add? Oh boy. Ooh, jeepers. Ten cuidado, Senor Fritz. Find the first 5 terms of a sequence. So which would you rather use then to find the first 5 terms of a sequence? Which form? Ben and Tyler?
Recursive.
Recursive, I would too. I'm gonna clone that. Yeah. I would rather use recursive. How come?
This is it. It's just easier to keep plugging in numbers instead because you're evaluating it more than once.
Yeah. Instead of having to plug in numbers repeatedly, that way we have to do it explicit, we could simply apply my pattern, right, to the first term and just do my rule plus 3, plus 3, plus 3 recursively to generate the first 5 terms. So I'm going to say easy to apply rule to previous term. For low term numbers like the first 5 terms. Awesome. And I'm thinking for PDFable, I like the little separated interrobang there, just for good measure. All right, let's go ahead and take a look at a real world application then. The first row of the auditorium has 15 seats. Each row has 3 more seats than the row in front of it. So picture an auditorium where the first row has 15 seats, and then each row has 3 more seats than the row in front of it. Can we write an explicit formula for the situation? Can we write a recursive formula for the situation? Well, absolutely. If I consider the number of rows in the the number of seats in the first row, there'd be 15 seats. How many seats then would be in the next row? Yeah, 18. Followed by a row that had 21 and 24, ... Right? And we don't know how big the auditorium is just yet. Let's write an explicit formula for the situation. So we've got 2 different ways we could write an explicit formula. We've got our a sub n equals a sub 1 plus d times quantity n minus 1. Or we've got our a sub n equals a sub 0 plus d times n. Either one is correct. However, the second one looks more like our slope-intercept form, y equals a plus bx. And so for that reason, many of you will like that form. Let's go ahead and do the first way. I know that a sub n would be given by a sub 1 is the first term, that's 15, plus my constant difference between seats would be how many? 3 times quantity n minus 1, so that would be one way. Or a sub n equals, this is an easier form to evaluate, but I need to get the zeroth row. And so the 0th row was not present. It's a ghost row. It's not really there, but I could get it by applying my pattern in reverse. What would a sub 0 be had there been a 0th row? Heather? 12. Good job. So we count backwards one pattern, and then plus dn, so this would be plus 3n. Either are correct. So we can do this either way. Next, let's write a recursive formula for the situation. So a recursive formula for the situation has 2 things, right? It's easy to recognize because we have a bracket. I need a start value, that is a sub 1, the number of seats in the first row, and I need a rule that gives us the current number of seats based on the previous number of seats. And so do I know a sub 1, the number of seats in the first row? Yeah, what's that? Aaron? 15, thank you. If I want to know the number of seats in the current row, I look at the one before it, call it a sub n minus 1, and do what to it? Add 3, absolutely. This is a recursive formula for the situation. Both of them have their utility, right? Both of them have their utility. If I wanted to list the first first rows, the number of seats in the first several rows, I'd rather use the recursive formula. If I wanted to know the number of seats in the nth row. If it was a big auditorium, then I'd probably want to know the explicit formula. Let's see what we're asked. List the number of seats in each of the first 5 rows. It looks like we almost already did that. I'll start with 15 and then plus 3, plus 3, plus 3. So let's do that. 15, 18, 21, 24, 27. How's that? If the last row has 78 seats, how many rows are in the auditorium? If the last row has 78 seats, how many rows are in the auditorium? That's a great question. Which formula do I want to use for that? Or do we want to use the explicit or the recursive formula for that? Bless you. Which formula would you rather use to figure out the answer to that question? Ben?
Explicit.
How come?
Because 78 is part of the number.
Yeah, I would have to keep track of, right, each of these rows and catalog them all the way up until I got to 78, and that could take a while. It's going to be much quicker and efficient to utilize my explicit formula since I have one. So let's do that. I'm going to plug in 78 seats, and where would that go? Would that go for the term number, or would that go for the number of seats? Number of seats. So let's go ahead and set my A sub n. My A sub n equal to 78 and solve for n to determine the row number. We'll go ahead and replace A sub n with 78. We'll solve for n by subtracting 12 from both sides. And I get n equals 66 divided by 3. Go gadget arm. So I'm getting 22. So it looks like there must be, what, 22 rows? 22 rows. In the auditorium. Awesome. What questions do you have about our seats in the auditorium rows? Problem situation. Okay. So for our practice today, you'll have an opportunity to earn 1 stamp at the end of your practice. I do have an answer key for this that you'll be able to come up and check. You may work with a partner as well. But first, I want to make sure that we have our closure taken care of. So everybody, let's continue with our note sheet. We'll complete the closure. I'll stop the recording then, and you'll have a chance to practice and earn an additional stamp while we're still in Unit 2. And we'll be doing our stamp check next time. So you want to make sure that you're earning all your stamps. Think, don't call out. What are 2 kinds of formulas for sequences? Which one do you prefer and why? Go ahead and write that down. How many parts does a recursive formula need, and what are those parts? True or false, a sequence is a relation. True or false, a sequence is a function. And unless otherwise specified, what is the domain for all sequences? Please have a written response for each of these and be ready to share with the whole class when I call on you. Okay, what are the 2 kinds of formulas? What are the 2 kinds of formulas that we have? Marina? Explicit formulas, good. Explicit formulas where I have a function rule that gives me the term value based on an input term number. And recursive, a recursive formula, which we'll talk about more in number 2. Which one do you prefer, explicit or recursive? Do you prefer explicit or recursive? Margot?
Explicit, because you can find any.
Yeah, in explicit, you can find any term, whether it's the first, the second, the third, or the 75th term, as we did. So explicit is a function rule, and we're accustomed to being able to evaluate a function rule, right? And so explicit definitely has its utility. Under what circumstances would we like recursive better? Well, if we're just asked to generate the first several terms, then I think recursive is easiest. So it depends, right? It depends on what we're trying to do. How many parts does a recursive formula need? So how many parts does a recursive formula need? And what did you get for that? Heather? 2 parts. Good. So there's 2 parts for a recursive formula. It's easy to recognize because of the brackets. What are those parts? Well, we need the first term for first term values. And we need a rule that gives the current term based on the previous term's value. So we need the first term, and we need a rule to get the current term based on previous. And that's totally going to fit right here. All right, true or false, a sequence is a relation. True or false, a sequence is a function. Oh, jeepers. So is a sequence a relation? So true or false, a sequence is a relation. Adam. That is true. The sequence is a relation because it could be written as ordered pairs, and all it takes to be a relation is to be a collection of ordered pairs. True or false, a sequence is a function. It's a sequence of function. Cody? Also true. Thank you. A sequence pairs input values that are term numbers with output values that are term values, right? Since there's only one term value for the third term, it has to be a sequence. There's no repeated, right? There's not multiple outputs for a given term number. The third term is 11 every time. Unless otherwise specified, what is the domain for all sequences? What's the domain for all sequences? Adam? Oh, that's my recursive definition. Only applies if I know the first term, but I'm starting with the first term, which is n equals 1 for the first term. Then going to n equals 2. And if I continued on, I'd have all of the counting numbers, or natural numbers. And so the domain for all sequences are the counting numbers, starting with 1, 2, 3, and so on.
Positive integers?
Yep, the positive integers. Good. Absolutely right. What questions do you guys have about our closure today? Okay, then I'm going to go ahead and stop the recording now, and we'll have an opportunity to practice with the part.